Okay, so at the previous lecture, we introduced Fredholm operators. So let's recall the definition. Suppose that we have vector spaces X and Y, and a linear operator T from X to Y. And we say that T is Fredholm. T is Fredholm if the kernel of T and the co-kernel of T are finite dimensional. So you see that the definition is purely algebraic. It makes sense for any linear operator between arbitrary vector spaces. But of course, we will be interested in this notion in the context of functional analysis. So we will be interested in the situation where X and Y are Banach spaces and T is bounded. Also, for each Fredholm operator, we introduced the index. So the index of T is, by definition, the dimension of the kernel minus the dimension of the co-kernel of T. And we proved the following important additivity property of the index, which states that if we have two operators, operator S, operator T from X to Y, and operator S from Y to Z, then the following formula holds. The index of ST equals the index of S plus the index of T. More exactly, the formula means the following. You have two operators, S and T, and if we look at the three operators, S, T, and ST, their composition, and if any two operators in all these three operators are Fredholm, then so is the third one, and this formula holds. So in particular, if you have two Fredholm operators, then their composition is a Fredholm operator, and we have this formula. So this is a very useful property of the index. Okay, so let's now concentrate on the situation where X and Y are Banach spaces and our operators are bounded. Our next result shows that the image of any Fredholm operator is always closed. Now, this result is due to Kato. So suppose that X and Y are Banach spaces, and T is a bounded linear operator from X to Y, such that the co-kernel of T is finite dimensional. I claim that the image of T is automatically closed in 1. The image of T is closed. So in particular, we see that the image of any bounded Fredholm operator is closed. To prove this result, first of all, let's observe that we may assume, without loss of generality, that the kernel of T is trivial. We may assume that the kernel is trivial. Well, indeed. Otherwise, if it is non-trivial, we may consider the induced operator from the quotient of X module of the kernel. So otherwise, we consider the operator say t hat, from the quotient module of the kernel to y, which is induced by t, in the sense that the following formula holds. Well, indeed, this operator t hat is always injective, so its kernel is trivial, and the image of t hat is equal to the image of t. So by using this trick, we reduce everything to the case where the kernel of our operator is trivial. So for convenience, we assume from the very beginning that the kernel of t is trivial. So now, since the co-kernel is finite dimensional, we can decompose y as the direct sum of two subspaces, namely the image of t and a finite dimensional subspace y0. Y0 is finite dimension. And let's consider the following operator S, which acts from the L infinity sum of x and y0. So let's recall that the L infinity sum is just the direct sum of x and y0, and the norm of a pair in this space is defined to be the maximum of the norms of the sums. So S acts from the L infinity sum to y by the following simple formula. It takes xy to tx plus 1. Well, since the kernel of t is trivial, it's immediate from the construction that S is bijective. S is bijective, and S is obviously bounded. For the simple reason that t is bounded. And now let's observe that S acts between Banach spaces. So Y is a Banach space, Y0 is a Banach space because it is finite dimensional. Well, a finite dimensional subspace of a normed space is always closed. And so in particular, it's a Banach space. And X is also a Banach space. And the L infinity sum of two Banach spaces is a Banach space. So S is a bijective bounded operator between Banach spaces. And let's now recall the Banach inverse mapping theorem, which states that a bijective bounded operator between Banach spaces is a topological isomorphism. So the Banach theorem implies that S is a topological isomorphism. Okay, let's now observe that if we consider X as a subspace in the direct sum, or more exactly, we consider the following subspace, X plus 0, which is canonically identified with X, then this is a closed vector subspace in the L infinity direct sum. This is a very easy exercise. So it is closed, and S is a topological isomorphism, that is a linear homeomorphism. And the homeomorphism always takes closed sets to closed sets. So we conclude that if we apply S to this subspace, then this will be a closed subspace in Y. But what is this? S applied to X plus 0 is nothing but the image of T, just by construction. And so we conclude that the image of T is closed. And this completes the proof. So in particular, this result implies that the image of any bounded Fredholm operator between Banach spaces is closed. Okay, our next result about Fredholm operators gives us a useful duality between the Fredholm property of an operator and of the dual operator. So we have the following theorem. Again, suppose that X and Y are Banach spaces, and T is a bounded linear operator from X to Y. Then I claim that T is Fredholm, if and only if the dual operator T star is Fredholm. And moreover, if they are Fredholm, then first of all, the index of T star is equal to minus the index of T. And second, the index of T can be calculated as follows. This is the dimension of the kernel of T minus the dimension of the kernel of the dual operator T star. This formula is sometimes useful when we want to avoid co-kernels for some reason. By the way, we already have a concrete example of this situation. At the previous lecture, we discussed one of the basic examples of a Fredholm operator, namely the left shift operator and the right shift operator on, for example, on the literal L2 space. And we know that the dual of the left shift operator is essentially the right shift and the other way around. So in some sense, they are dual to each other. And the index of the left shift is equal to 1, and the index of the right shift operator is -1. But in the general case, we have this formula. That is, the index of T star is minus the index of T. Okay, to prove this result, let's observe that if either of the operators T and T star is Fredholm, if either T or T star is Fredholm, then T satisfies the conditions of the closed image theorem. The closed image theorem, let's recall that it states in particular that if we have a bounded linear operator between bounded spaces, bounded linear operator T between bounded spaces, then the image of T is closed, if and only if the image of the dual operator is closed. If T is Fredholm, then the image of T is closed by Kato's theorem. And if T star is Fredholm, then the image of T star is closed. But in both cases, the closedness of the image of T and of T star are equivalent to each other. So we conclude that in this case, the image of T and the image of T star are closed vector subspaces of of Y and X star respectively. They are closed, and also the closed image theorem implies that the kernel of T star is isomorphic to the dual of the co-kernel of T. And similarly, the co-kernel of T star is isomorphic to the dual of the kernel of T. This also follows from the closed image theorem. But now these two formulas readily imply that both the operators T and T star are Fredholm, and moreover, properties 1 and 2 are satisfied. 1 and 2 hold. Well, indeed, let's look at the statement. if, for example, if we know that T is Fredholm, then the kernel of T and the co-kernel of T are finite dimensional. But now these two formulas imply that the same is true for the operator T star. So the co-kernel of T star and the kernel of T star are finite dimensional. And so T star is Fredholm. And the other way around, if we know from the very beginning that T star is Fredholm, then this space is finite dimensional and this one is finite dimensional. And if we look, for example, at the kernel of T, so the kernel is, we see that the kernel has the property that the dual of the kernel is finite dimensional. But it's very easy to see that if the dual of a normed space is finite dimensional, then the space itself is also finite dimensional. So we see that the kernel of T is finite dimensional, and the same argument shows that the co-kernel of T is finite dimensional. So T is Fredholm. And finally, the same two isomorphisms imply formulas 1 and 2. For example, the index of T is the dimension of this space minus the dimension of this space. And since the dimension of the dual is the same as the dimension of the original space, we conclude that, well, the index of T star is the dimension of this one minus the dimension of this one. And this is exactly minus the index of T. And for the same reason, formula 2 holds. So the index is the dimension of the kernel of T minus the dimension of the co-kernel, but the dimension of the co-kernel is equal to the dimension of the kernel of T star because of this isomorphism. Okay, so this completes the proof. Well, now our next goal is to discuss a piece of theory which chronologically was created long before the notion of a Fredholm operator was introduced. This theory was created mostly by Riss in 1918, and some additional results were also obtained by Schauder in 1930. And now the union of their results is usually called the Riss-Schauder theory. This theory is very important, not only in functional analysis, but also in some important applications, in particular to integral and differential equations, and to some infinite dimensional geometry. Some people even say that the Riss-Schauder theory is the absolute highlight of functional analysis in general Banach spaces. The quintessence of this theory can be stated as follows. If we have a compact operator K on the Banach space, then the operator 1 plus K, where 1 is the identity operator, the operator 1 plus K is Fredholm, and the index of this operator is 0. Now, of course, this is not the whole theory by Riss and Schauder, but this is the most important part, the most important statement of this theory. If K is a compact operator, then 1 plus K is Fredholm, and the index of 1 plus K is 0. So to begin with, let's introduce some purely algebraic notions. Well, by the way, before we do it, I must also say that well, we see that the Riss-Schauder theory provides a rich supply of Fredholm operators of index 0, and actually this theory was one of the main motivations for Dieudonné, who introduced the general notion of a Fredholm operator in the 1940s. So this is one of the main sources of Fredholm operators. Okay, let's now introduce some notation. Suppose that X is a vector space and T is a linear operator from X to itself. So we introduce the following notation. For each non-negative integer n, we denote by kn the kernel of T to the power n, and we denote by Rn the image of T to the power n. So we obtain two chains of vector subspaces. The ascending chain of the kernels and the descending chain of the images. And it can happen that some of them stabilizes at some step. And there is a special terminology for this phenomenon. So we define the ascent of T to be the following number. So this is the minimum integer n, such that kn equals kn plus j for each non-negative j. And if there is no such n, if the first chain doesn't stabilize, then we say that the ascent is equal to infinity. And similarly, we define the descent of T is the number d of T defined by the following formula. This is the minimum n such that Rn equals Rn plus j for each non-negative j. And similarly, we say that the descent is infinite if there is no such n. In Russian, ascent is подъем. Descent, спуск. Okay, so let's start with this following simple algebraic lemma. Lemma 1. First of all, I claim that if for some n, kn equals kn plus 1, that the chain of the kernels actually stabilizes at the same step. Then kn equals kn plus j for each j. And hence this implies that the ascent of T is finite. The same result holds for the images. So if Rn equals Rn plus 1 for some n, then the chain of the images stabilizes at the same step. And hence the descent of T is finite. And finally, part 3, I claim that if T has a finite ascent and finite descent, then actually the ascent equals the descent. So these numbers are the same if they are finite. It's very easy to construct examples of operators for which the ascent is finite, but the descent is infinite, and the other way around. But if we know that both A of t and D of t are finite, then they are equal. Well, the lemma is actually very easy. This is just simple linear algebra. Well, for example, let's prove part 1. Well, to show that the chain of the kernel stabilizes, it suffices to show that kn plus 1 equals kn plus 2. Then we just use the induction on n. So we assume that kn equals kn plus 1, and we want to show that kn plus 1 equals kn plus 2. So let's take a vector in kn plus 2, say little x. Tn plus 2 of x is 0. Tn plus 2 of x is tn plus 1 applied to t of x. So this implies that t of x sits in kn plus 1. T of x sits in kn plus 1, but by assumption kn plus 1 is equal to kn. So we see that t of x sits in the kernel of t to the power n. And so tn plus 1 of x, which is nothing but tn applied to t of x, this is 0 because t of x sits in kn. And as a result, we deduce that x sits in kn plus 1 because tn plus 1 of x is 0. And that's it. So we proved that any vector in kn plus 2 actually belongs to a kn plus 1. So this completes the proof of part 1. Part 2 is very simple. It's similar to part 1. So this is an exercise for you. This is also very easy. And to prove part 3, I'll actually prove only half of part 3. So let's show that, for example, A of t is less than or equal to D of t. And the proof of the opposite inequality is similar. To prove this inequality, let's assume that this is not the case. Suppose that A of t is bigger than D of t. And let n denote A of t minus 1. Well, okay, so what does that mean? N is smaller than A of t. So we see that Kn is properly contained in Kn plus 1. And n plus 1 is already A of t, so Kn plus 1 is equal to Kn plus 2. And on the other hand, since D of t is smaller than A of t, we conclude that In equals In plus 1. So we want to deduce a contradiction. So to deduce a contradiction, let's take an element in Kn plus 1. Let X be an element in Kn plus 1. And let's look at T n of x. Well, T n of x obviously belongs to In, which is equal to In plus 1 by assumption. And this implies that T n of x can be written in the form Tn plus 1 of y for a suitable vector y, for some y in x. Okay, now by assumption x sits in Kn plus 1. So if we apply t to the power n plus 1 to x, then we get 0. And this is equal to t to the power n plus 2 of y. Now this means that y sits in Kn plus 2. Y belongs to Kn plus 2. And by assumption, Kn plus 2 is equal to Kn plus 1. So if we apply t to the power n plus 1 to y, we get 0. But Tn plus 1 of y, Tn plus 1 of y is equal to Tn of x. And so x belongs to Kn. So we see that an arbitrary vector which belongs to Kn plus 1 actually belongs to Kn. So we deduce that Kn plus 1 is equal to Kn. And this is a contradiction, because we have already assumed that this inclusion is proper. So the contradiction implies that actually we have this inequality. The ascent is less than or equal to the descent. And the opposite inequality is a little exercise for you. The proof is similar. Okay, so this is lemma 1. Lemma 2. Lemma 2 is also purely algebraic. And it's called the abstract race decomposition, or the algebraic race decomposition. So it's a useful property of operators with finite ascent and finite descent. So we suppose again that T is a linear operator from X to itself, where X is a vector space. And suppose that the ascent of T and the descent of T is finite. So in this case, lemma 1 implies that they are the same. So let's denote this number by P. P is the ascent of T, and it is also equal to the descent of T. Let Kp denote the kernel of T to the power P. And Ip, let Ip denote the image of T to the power P. I claim that both Kp and Ip are T-invariant subspaces. This is more or less immediate from their definition. X is equal to their direct sum, which is not entirely obvious. Next, the restriction of T to Kp is nilpotent. And the restriction of T to Ip is an isomorphism of IP onto itself. So this is algebraic Riesz decomposition. Actually, the decomposition is here. So Lemma 2 states that if our operator has finite ascent and finite descent, then this operator has a particularly interesting structure. It's the direct sum of two pieces, an nilpotent operator and an isomorphism. So this is a structure of operators with finite ascent and finite descent. Okay, so this is the algebraic Riesz decomposition. And let's now try to prove Lemma 2. Well, it's clear that from the construction that Kp and Ip are T invariant. Clearly, they are T invariant. And it's also clear that the restriction of T to Kp is nilpotent. Just because Kp is the kernel of T to the power P. So let's now show that X is the direct sum of Kp and Ip. So let's take an element X in our space, and let's apply T to the power P to X. Well, T to the power P of X clearly belongs to Ip. And by construction, Ip is equal to I to P. So this implies that Tp of X is equal to T to the power 2P of Y for some element Y in our space. So let's draw a picture for convenience. So this is X. This is T to the power P of X. So we apply T to the power P. And this is Y. Okay, so let's now apply T to the power P to Y. And let's denote the result by X prime. So this is X prime, which is equal to T to the power P of Y. It's clear that if we apply T to the power P again to X prime, then we get Tp of X. So this is T to the power 2P of Y, which is equal to T to the power P of X. If we now look at the difference X minus X prime, we conclude that this element sits in Kp. X minus X prime belongs to Kp. And so we can now write our original element X as the sum X minus X prime plus X prime. So we know that X minus X prime sits in Kp, and by construction, X prime sits in Ip. So we see that X belongs to the sum of Kp and Ip, and since little x was arbitrary, we conclude that X, the space X, is the sum of Kp and Ip. Okay, let's now show that this is actually the direct sum. That is, the intersection of Kp and Ip is 0. So suppose now that little x sits in the intersection of Kp and Ip. So this implies that on the one hand, Tp of x is 0, because x is in Kp, and on the other hand, x can be written in the form t to the power p of z, for some little z in x. If now apply t to the power p to x, well, this is 0. But on the other hand, this is t to the power 2p of z. So we conclude that z sits in k2p, in the kernel of t to the power 2p, k2p. But p is equal to the ascent. And so k2p is equal to kp. And therefore, t to the power p of z is 0. That is, x is 0. So we conclude that the intersection of Kp and Ip is 0. And so x is indeed the direct sum of Kp and Ip. Okay, now to complete the proof, let's look at the statement. To complete the proof, we have to show that the restriction of T to Ip is an isomorphism of Ip onto itself. Well, why is it an isomorphism? First of all, by construction, if we apply T to Ip, what we get is exactly Ip plus 1, just by definition. But Ip plus 1 is equal to Ip by assumption. And so this implies that if we restrict T to Ip, then this map takes Ip onto Ip. That is, this restriction is surjective. Well, now why is it injective? Well, we already know that the intersection of Kp and Ip is 0. And the kernel of T, which is just K1, is contained in Kp. So this implies that the kernel of T, the intersection of the kernel of T and Ip is also trivial. But this means exactly that T restricted to Ip is injective. And as a result, we conclude that T restricted to Ip is an isomorphism of Ip onto Ip. And this completes the proof of Lemma 2. Okay, so Lemma 1 and Lemma 2 are useful algebraic preliminary results. And now we are ready to prove the most important part of the Riesz-Schauder theory. So the following theorem is due to Riesz. This theorem was proved in the same famous paper by Riesz, where he introduced the modern definition of a compact operator and proved many useful results about these operators. And once again, I'd like to recall that Riesz considered only the space of continuous functions on a closed interval, for the simple reason that in 1918 there was no general notion of a Banach space. But amazingly, almost all proofs given by Riesz hold in the case of an arbitrary Banach space. Okay, so now suppose that X is a Banach space. X is a Banach space, and T is a bounded linear operator on X, which has the following special form. It is a compact perturbation of the identity operator. That it has the form 1 plus a certain compact operator. Then we have the following results. First of all, I claim that T is Fredholm. T is Fredholm. There's a question about the nilpotence of T restricted to Kp. Well, let's look once again at the proof of Lemma 2. What is Kp? Kp is, let's look at the definition. Kp is the kernel of T to the power P. So just by this definition, if we restrict T to Kp, then the pth power of this restriction is 0. Just because Kp is the kernel of T to the power P. It's just a corollary of the definition. Okay. Okay. So now the first part of his theorem states that if T is a compact perturbation of the identity operator, then T is Fredholm. T is Fredholm, and the index of T is 0. This is probably the most important part of this theorem. Second, I claim that T has finite ascent and finite descent. And part 3 is also quite useful. This is also a version of the Is decomposition. Let P denote the ascent of T, which is equal to the descent of T. As before, we denote by Kp the kernel of T to the power P, and we denote by Ip the image of T to the power P. Then I claim that Kp and Ip are closed and T-invariant subspaces. Closed is also essential. Closed T-invariant subspaces. Well, it's clear that the kernel is closed. The kernel of any bounded operator is closed, but the image is not always closed. So the statement that Ip is closed is quite interesting here. So they closed and T-invariant. X is the direct sum of Kp plus Ip. Kp is finite dimensional. Kp is finite dimensional. T restricted to Kp is nilpotent. And T restricted to Ip is a topological isomorphism of Ip onto itself. And this is the Is decomposition. So if we compare this part 3 with the previous lemma, we see that there is some more information here, namely that Ip is closed and Kp is finite dimensional, and T is a topological isomorphism, not just a vector space isomorphism, but is a topological isomorphism of Ip onto itself. Okay. Well, since T is of the form 1 plus a compact operator, let's write explicitly T in the following form: 1 minus S, where S is a compact operator. It will be more convenient to write minus instead of plus. Clearly, this is equivalent. Well, the proof will be divided into several steps. As a first step, let's show that the kernel of T is finite dimensional. The kernel is finite dimensional, and the image of T is closed. Formally, if we could prove that T is Fredholm, then the image of T would be closed by Cato's theorem, which was proved some time ago. But for technical reasons, it will be more convenient to prove, first of all, that the image of T is closed, and then to deduce that T is Fredholm. Well, why is the kernel of T finite dimensional? Let K denote the kernel of T. And since T equals 1 minus S, we conclude that the restriction of S to K is actually the identity map of K. But on the other hand, S is compact, and therefore the restriction of S to K is also compact. And we already know that the identity operator is compact, even only if it acts on the finite dimensional space. So this implies that K is finite dimensional. Okay, let's now show that the image is closed. To show that the image is closed, we consider the induced operator, that's denoted by T hat, which acts from the quotient modulo of the kernel to X by the following formula. Well, the image of T hat is equal to the image of T. And so to show that the image of T is closed, it suffices to show that T hat is topologically injective. Well, indeed, a topologically injective operator between Banach spaces obviously has closed image, because the image is topologically isomorphic to X, and X is a Banach space. So it suffices to show that T hat is topologically injective. And let's recall that an operator is topologically injective, that is, it is a topological embedding, even only if it is bounded below on the unit sphere. That is, there is a positive constant C such that the following inequality holds everywhere on the unit sphere of the quotient of X modulo K. So this property is equivalent to the topological injectivity. And let's suppose that there is no such C. Assume there is no such C. Well, this implies that we can find a sequence. There is a sequence on the unit sphere of the quotient, was denoted by UN. The norm of UN is 1, so it's on the unit sphere, such that T hat of UN goes to 0. For each n, let's choose a representative of UN. So let's write UN in the form xn plus k, where xn belongs to big X. And we may also assume that the norm of xn is less than or equal to, say, 2. Just by the definition of the quotient norm, we can find a representative of almost the same norm. Then what can I say about xn? The norm of the quotient, that is, the norm of UN is 1. And this means that the distance between xn and k, the distance between xn and k is nothing but the norm of UN. So this is 1. And T hat applied to UN is nothing but T applied to xn. So Txn goes to 0. Okay, now Xn is bounded. Xn is a bounded sequence, and S is a compact operator. So the sequence, if you apply S to Xn, then the resulting sequence has a convergent subsequence. And by passing to the subsequence, we may assume from the very beginning that S of Xn converges. We may assume that Sxn converges to some element of X, because S is compact. If this sequence doesn't converge, then we just choose a convergent subsequence. Well, Sxn converges to X, that is Sxn, what is this? This is Xn minus Txn. Xn minus Txn converges to X. But we already know that Txn converges to 0. And so this implies that Xn converges to X. Xn converges to X, and by continuity of T, we see that Txn converges to T of X. But we already know that Txn converges to 0. And so this implies that T of X is 0. T of X is 0. That is, this means that X sits in the kernel of T. X belongs to K. K is the kernel of T, and X belongs to K. But on the other hand, the distance between Xn and K is 1, and Xn converges to X. This is obviously impossible. So this distance is 1, Xn converges to X, but X belongs to K. This is obviously impossible. This is a contradiction. This is a contradiction. And the contradiction implies that T hat is topologically injective, and therefore the image of T is closed. Okay, so this is the end of step 1. So we have proved that the kernel is finite dimensional and the image is closed. The second step is to show that T is Fredholm. Step 2, T is Fredholm. Well, we already know that the kernel of T is finite dimensional. Now we have to show that the co-kernel of T is finite dimensional. We know that the image of T is closed. The image of T is closed. And so the co-kernel of T, which is the quotient module of the image, is a Banach space. The co-kernel of T, which in general is just a semi-normed space, the quotient of a Banach space modular vector subspace is a semi-normed space, and it is normed and actually is a Banach space if and only if the subspace is closed. So in this case, we conclude that the co-kernel of T is a Banach space. And we want to show that it is finite dimensional. But the closed image theorem, applied to T implies that the dual of the co-kernel is isomorphic to the kernel of T star. And what can you say about T star? Where T star is 1 minus S star. So this operator is also the form 1 plus a compact operator. And for such operators, we already know that the kernel is finite dimensional. by step 1. The kernel of T star is finite dimensional. And now finally, this isomorphism implies that the co-kernel of T is also finite dimensional. And finally, we conclude that T is threadable. This is the end of step 2. Now, before proving that the index of T is 0, let's show that T has finite ascent. This is step 3. T has finite ascent. Well, why is it so? Assume that this is not the case. Assume that the ascent of T is infinite. This implies that the chain of the kernels is strictly increasing. Kn is properly contained in Kn plus 1 for each n. And now we apply the Epsilon perpendicular lemma, which is also due to Riss, and which was proved in the same famous paper. And we choose an 1/2 perpendicular. Choose xn in Kn plus 1. Which is 1/2 perpendicular to Kn. Let's recall that this means that the norm of xn is 1, and that the distance between xn and Kn is greater than or equal to 1/2. So we would like to obtain a contradiction. Namely, we will get a contradiction with the compactness of S. So we take any pair of indices n and m. For convenience, we suppose that n is bigger than m, and is greater than or equal to m plus 1. And let's do the following. Let's try to estimate the distance between Sxn and Sxm. So we'll try to show that this distance is bounded away from 0. If this distance is bounded away from 0, we'll get a contradiction with the compactness of S. Well, what is this? S is 1 minus T. S is 1 minus T. So this element can be written as follows. So this is xn minus txn plus xm minus txm. Well, now xn belongs to Kn plus 1. And this implies that T of xn belongs to Kn, just because Kn is the kernel of T to the power n. So this vector belongs to Kn. And as for xm and txm, xm belongs to Km, and Km, it belongs to Km plus 1. It belongs to Km plus 1, but Km plus 1 is contained in Kn because n is greater than or equal to m plus 1. And the same is true for T of xm. So as a result, we see that all these three vectors, txn, xm, and txm, belong to Kn. And xn, by assumption, is 1/2 perpendicular to Kn. So because of this inequality, we conclude that this distance is greater than or equal to 1/2. And this is a contradiction with the compactness of S. contradiction with the compactness of S. Okay. So we see that T has finite ascent. Step 4. T has finite descent. To prove this, we use a nice duality argument. So we already know that T star is also of the form 1 plus a compact operator. So we already know that T star has finite ascent. And so there exists a non-negative integer n such that the kernel of T star to the power n is equal to the kernel of T star to the power n plus 1. Okay, now let's take the pre-annihilators of these subspaces. And we also use the obvious fact that the dual of T star to the power n is equal to the dual of T to the power n. So these two spaces are the same. And so their pre-annihilators are also the same. But the pre-annihilator of the dual operator is equal to the closure of the image of the operator. This is true for any bounded linear operator between normed spaces. And finally, we can remove the closures here because we already know that T is Fredholm. And so all the powers of T are also Fredholm. And therefore, the images are closed. And that's it. So we see that the image of T to the power n is equal to the image of T to the power n plus 1. And therefore by lemma 1, the descent of T is finite. And finally, step 5. This will be the final step of our construction. We have to show part 3. Let's look again at the statement. We have to prove there is decomposition here. And we have to show that the index of T is 0. For example, why? Well, first of all, we know that T is Fredholm. T is Fredholm. So T to the power P is also Fredholm. And so IP is closed. And for the same reason, KP is finite dimensional. This follows from the fact that T to the power P is Fredholm. T is Fredholm. So is T to the power P. And this implies that KP is finite dimensional. And that the image of T to the power P, that is IP, is closed. And now we can apply lemma 2. And we see that lemma 2 implies part 3. The only point is to observe that the restriction of T to IP is a topological isomorphism because it's a bijection between a bounded linear operator, bijective bounded linear operator between Banach spaces. This implies 3 modulo the Banach inverse mapping theorem. well, not modulo, actually, by the Banach inverse mapping theorem. It's just combine Lemma 2 and the Banach inverse mapping theorem. Okay, and finally we have to show that the index is 0. But we already know that the T is consists of two pieces. It's the direct sum of T restricted to Kp and of T restricted to Ip. And it's clear that the index of such a direct sum operator is equal to the sum of the indices of T restricted to Kp plus the index of T restricted to Ip. But the first sum on the 0, because the space is finite dimensional, and the second sum on a 0, because T restricted to Ip is an isomorphism of Ip onto itself. And so we conclude that the index of T is 0. And this completes the proof of our theorem. This is the end of step 5, and this is the end of the proof of the theorem. Well, in conclusion, let's look at some corollaries of this result. Corollary 1 is the abstract Fredholm alternative. If T is an operator of the same form, a compact perturbation of the identity operator, then this operator is injective, even only if it is surjective, even only if it is bijective. And this is immediate from the fact that this operator is a Fredholm operator of index 0. So the kernel is trivial, even only if the co-kernel is trivial. And corollary 2 is due to Schauder. And this corollary contains the abstract Fredholm theorems. The classical Fredholm theorems are some results about integral equations, and Schauder's observation together with Rees' theorem gives an abstract form for this result, for Fredholm's theorems. Again, we suppose that T is an operator of the same form, the identity map plus a compact operator. Then, first of all, the dimension of the kernel of T is equal to the dimension of the kernel of T star. And this is a finite, and these spaces are finite dimension. Second, the image of T is equal to the pre-annihilator of the kernel of T star. And finally, the image of T star is equal to the annihilator of the kernel of T. So this is if we apply this result to an operator of the form 1 plus k, where k is the Hilbert-Schmidt integral operator, and formulate this result in terms of equations of the respective integral equation, of the solutions of the respective integral equation, then we get the classical Fredholm